So let me give the brief introduction of our resource person of today's first session. Dr. Mahesh Kumar has received MTech degree in solid state materials from IIT Delhi and PhD degree in engineering from IISc Bangalore. He worked at Central Research Laboratory of Bharat Electronics Limited, Bangalore as scientist from 2005 to 2013. He has received INSA Medal for Young Scientist 2014 by Indian National Science Academy, the MRSI Medal 2016 by Materials Research Society of India, DA Young Achievers Award 2016 by BRNS, and Research Excellence Award 2020 by IIT Jodhpur. He is the recipient of the Fulbright Nehru Academic and Professional Excellence Fellowship 2021 to work at MIT, USA, the Royal Society International Exchange Award 2021 to work at University of Edinburgh, UK, JSPS Invitation Fellowship 2020 work to work at Nagasaki University, Japan, PIFI Visiting Scientist Fellowship 2021 by Chinese Academy of Science to work at Hefei Institute of the Physical Science, China, Duo Indian Professor Fellowship 2020 to work at University of Stuttgart, Germany, Bhaskara Advanced Solar Energy Fellowship 2018 to work at South Dakota State University, USA, and INSA DFG International Bilateral Exchange Award 2015 to work at the University of Paderborn, Germany. He is also editorial board member of IEEE Sensors Journals and Nano Express IOP Publishing. He is founding member and served as a chair of Indian National Young Academy of Sciences. Dr. Kumar is member of Program Advisory Committee of SERB and DST. He has published more than 130 research articles. His research interests are focused on 2D materials, nanomaterials, sensors, semiconductor materials, and devices. So once again, sir, I heartily welcome you, and the mic is over to you for the session.
Yeah, thank you very much for inviting me for this talk. So 1 minute, I can share the slides. Yeah, can you see my slides?
Yes, sir.
Okay, yeah, thank you very much. And yeah, good morning, all the participants. And today I'm going to talk about the 2D materials. These are the new type of the new nanomaterials. How we can use these nanomaterials for the different applications. I think other resource person, they have discussed this one, but mainly I'm going to talk about this one. How we can make the sensors, and mainly I am going to talk about the water sensors. How we can use these nanomaterials to make the heavy metal ion sensors. So if you talk about this one, water requirement for our human body, at least we required around 60% because our body, this one is having around 60% of water, and the rest we have the other elements here. And in the different part of the body, basically, this one is the different percentage of the water. For example, in the lungs, around 90% water, in brain, 75%, in the skin, 80%. So that means this water is essential for the all living, basically, this one, human and animals, or even for the plants here. This one is the necessary. So we need basically the clean water. And today, if you talk about the water quality, this one has really degraded. And the main, this one, you can say, basically the main source of this contamination is that one is the human, because this one throw steps in the water, and this pollution starts from the surface water by throwing these steps, and then this mix with the groundwater and destroy the complete our these water resources. So one thing is there, how to clean. I think all of us, we have heard this one, Ganga is dirty or Yamuna is dirty, because of this one throwing this one steps. Also these industries, they are basically release this used water directly in these rivers, and without doing the filtration. And because of this one, our water resources, they are really basically polluted here. If you talk about the pollution, broadly we can divide this pollution in 3 categories. One is the pathogenic organism is there, and second one is the organic this one materials from the fertilizer, desert, and sewage. And third one is the heavy metal ions. And these heavy metal ions, basically, they are in toxic in nature. And today, for many applications, we are using these heavy metals. For example, in the textile industry, we are using mainly the lead-based dyes. So this lead is there. This one is the highly toxic. Again, in agriculture, we are using pesticides. In mining industry, for different applications, we are using these heavy metals. And what is happening? These heavy metals, basically, they mix with the rainwater and reach to the our water reservoirs here and destroy the complete this one water circulation, because whatever water we are getting, that we are getting either from the lake, river, or whatever this one resource, this one water source is there. So overall, this one water quality is there. That one is this one polluted here. And this one we can see even in electronic and print media. This one, for example, Yamuna is this one highly polluted, and they have the different type of this one heavy metal, this one toxicity. Simply this one similarly, this one Chambal is there near to Kota. That one is also this one highly polluted, because many on the river, basically there are many these chemical industries, and they basically release their used water, and now the overall this here the water quality is there, that one is degraded. Same in the West Bengal, we have this arsenic polluted. So in the different part of the country, there are different type of the heavy metals, depend on the industry what we are using. Sometimes they are from the natural, for example, from the soil, they are mixing in this water here. If we overall across the country, if we see the water quality today, how we are measuring, how these water purifier companies, suppose if you buy a water purifier, what they will do? They will check only the TDS. What is the TDS? TDS is the total dissolved solids, this one, and one limit is there. For example, this one is below 480, this one milligram per liter. We say this water is the very good is there. So here you can see this one very good, this one fair, poor, and if this is above around 1900, we call this one is the unacceptable is there. And if you talk about the Rajasthan and Gujarat, in this particular region, basically this water TDS level is the very. But how we are measuring the TDS? I request this one participants.
Participants, please keep your mic on mute. So wait a minute, I'll do this.
Yes, and if you have any question in between also, you can ask me this one here. Okay.
Sir, wait a second, just I'm looking at it.
Yes.
Participants, please keep your mic on mute.
Okay. I think you can mute this one to everyone. Yeah.
Yes.
Yeah, thank you. Thank you. Yeah, so basically, if we see this one, how we are measuring this one TDS, simply we are measuring the conductivity. So between two electrodes, basically, how much this one conductivity is there. Based on this conductivity, we can measure the TDS. But this one is the basically TDS is there. But there is high possibility that TDS is low, but still these heavy metal ions, they exist in the water here. And now if you see all these purifier companies, basically what they are doing, okay, they are saying, okay, you have to change your cartridge basically after 1 year or 6 months, or basically they have the based on the water flow, how much water flow is there. For example, that one is this 1000 liter or 1500 liter is there, automatically you will get one indicator, this one. But actually there is a no real time this one detection, or you can say the sensor inside this one. We can make sure this one, whatever water we are drinking, that one is the safe here. So if you talk about these heavy metal ions here, few heavy metals, this one, they are essential for the human body. For example, copper, zinc, this one, iron and silver in a certain quantity, this one. So many times this one, for example, if you have some deficiency, iron or zinc deficiency during the COVID time, here doctors mostly they have recommended the zinc deficiency, so they have given the zinc additional basically supplements here. So these heavy metals, they are essential for human body in this basically certain limit here. But other heavy metals, they are highly toxic. For example, lead here, if you talk about this limit is around 1 ppb, cadmium and this one lead is around 5 ppb. So these basically heavy metal ions, they should be below this limit as defined by the WHO here. So now how to measure this one? Because when we are measuring the conductivity here, when we are measuring the TDS, we are measuring only the conductivity. And there is high possibility this one, because if you have, for example, when mercury, if you have around 10 ppb, this one, in that case, what will happen? If TDS is low, then also here this conductivity will not change from the 10 or 50 ppb, this one. So how to detect particularly these heavy metals? So first here, when we are making any sensor, biosensor, gas sensor or water sensor, these are the basically characteristics that we need this one. How much is that this one? Sensitivity is there. Whatever electrical quantity we are measuring, this one, when there is a change in the input quantity is from the real world we are getting what, for example, in this case is the concentration of heavy metal ions here. So whenever this heavy metal ions concentration is changing here, how much is the change in the output? That one is called the particularly this one sensitivity is there. Another one is the selectivity. Sensor should be selective, response should be fast. Again, the cost, compact. Otherwise, by ICP, because cost is very important here. Otherwise, we have done the lab equipment. We have ICP. This one by ICP mass spectrometer is there. We can measure basically in the at laboratory scale. But that cost is very high, around 30 to 40 lakh rupees we have to spend. That means in the house we cannot afford, even basically very difficult to afford in each city, or if you want to monitor at each level, this one. But at the laboratory level, we can use the ICP, and then we can measure basically how much these heavy metals are present here. So depending on this one, also depending on the, because compact, this one ICP is again the big here. So these are the basic this one parameters to design any type of the sensor here. And now here, when we are making basically any sensor, we have to see basically what is the physical or chemical phenomena is there. By using that here, we can detect. Okay. So here we can use, one is the electrochemical method is there. By using this one, we can detect this one. Biochemical methods also we can use, or colorimetry we can use. But by using these three methods, we cannot do the real-time monitoring. Okay, for the laboratory purpose here, we can collect the sample and then we can detect this one. But in this one, in water purifier, if you want to this one mount the sensor, we need the real-time monitoring. Similarly, for example, our river is there. If you want to monitor this one here, basically how much these heavy metals are present, basically we need the real-time monitoring sensor. Another, because mostly these industry, when they release the water, basically government, this one does not have the sensors, they cannot detect. Okay, these always there are the guidelines. Basically these industries, they have to clean the water and then they have to discharge, but they are not doing this one. So if we have basically can develop this sensor, we can mount these sensors and then we can do the monitoring. So fourth one is, this one is the semiconductor based sensors here. In the semiconductor based sensors, what is happening, this one, we have the field effect transistor here. So in the field effect transistor, between the source and drain, basically this one, your current is changing. So FET is working similar to like this one, your water tap is there. We have one gate basically here, and by the gate we are controlling the here flow, similar to the this one tape is there in the this one water flow we are controlling by the tapes. Similarly here in the field effect transistor, these carriers flow we control by the gate, and here on the gate we are applying the voltage. So in these sensors, what we are doing particularly at the gate, this one, we are using some functional nanomaterials, and now when these functional nanomaterials, they are absorbing the ion, basically how your potential is formed by the ions, and when these ions basically, for example, positive or negative ions, they are here at the gate. Basically, because of these ions here, electric field will this one generate, and because of this electric field or potential here, this current will change. So we can use this concept here, and by using this concept we can make these one heavy metal ions sensors here. So these ions, we need some nanomaterials. These nanomaterials can trap basically, or can absorb these ions, and when these ions are absorbed at the gate, basically the current between source and drain will change. So at IIT Jodhpur, we are trying to develop this sensor similar to the glucometer, how we are getting in the glucometer. For example, this one where we are this one putting one blood drop here, we get this one, how much is the sugar level is there in our body basically. Similarly here, if we have some device, portable device, small device, and whenever we are traveling, we can carry, for example, at the railway station or bus stand, when we buy this one, again we have to trust on the brand, Bisleri or this one, whatever this one brand is there, we trust this water is good, but we don't have the actually real-time monitoring system. But if we have some devices, we can put one water drop, this one, and then here we can test this one, this water is drinkable or not drinkable, this one. And similarly, these sensors also we can mount with the this one aqua purifier, and then we can do the real time monitoring. This one we can similar to this one other, basically we can make one display and we can get this one. Okay, whatever water we are drinking, that one is the safe is there. So now here, what material we have to use this one here? So we can use the 2D materials. What is the 2D materials? These are two-dimensional materials. That means here in these materials, basically we have the two-dimensional here, X and Y, you can say, and in Z direction, these are having the monolayers, this one. So in one direction, in the Z direction, there is a confinement is there, but electrons, this one carriers are free to move in X and Y, but they cannot move in the Z direction because potential is very high. Or you can say this one is the like one thin sheet is there. We can move only in X and Y direction, and third direction we have the confinement. So what is the advantage of these materials? We know there is a, because of the quantum confinement, basically we have the basically we have movement only in two direction, not in third direction here. So what is the advantage? This one, because general concept is there, basically confinements makes the this one mobility low. That's why, for example, criminals we are putting in the jail, because we are reducing their mobility. And how we are reducing their mobility? We put in a limited space here. So when we do the confinement, basically this confinement makes the mobility low. But in materials, electronic concept is there, that one is opposite. As per this one electronic concept, basically when we are doing the confinement, mobility is high, and the best example is that one is the graphene here. So when we are using bulk carbon material, in bulk carbon material here mobility is low, but when we are using one single layer of carbon layer, mobility is very high, that we call the graphene, or similarly your carbon nanotubes are there. So when we are this one reducing the dimension, mobility is high. So if mobility is high, mobility decides the speed of the devices. So in the sensors, if mobility is high, that means here our response time is there, that will be the short. And we want basically in the sensors, immediately whenever there's some physical phenomena is happening, immediately we should detect this one. So in that case, that means our device speed will be high. So whenever, for example, in the water some ions are coming, our sensor should give the signal here. So if mobility is high, one advantage is that sensor's response will be fast here. So this one is the first advantage, and why mobility is high, that we can understand by using this schematic diagram is there. So suppose this one is the bulk material is there, and these are the our carriers. We can say these are the electrons, and then we have the lattice points in this one. So you can see in this schematic diagram, basically electrons, they cannot freely move basically, because there are the lattice points, this one, there are atoms basically, and now these electrons, there is a lot of scattering is happening, and because of this scattering, overall mobility is there, that one is less as compared to the 2D materials, because in 2D materials we have confined basically. Now these carriers can move only in one direction. And when these carriers can move in only in one direction, their mobility is very high. Also, we can understand this one. For example, if you are going from Kota to Jaipur, one you are going by road, another you are this one follow this one random path. So in random path, what will happen? There is a lot of scattering, because how to monitor this one, in which direction we have to go. And when we have defined path, when we have the road, basically, we can directly, we can go, we can follow. So overall, the mobility will be high, this one. So by using this model, we can understand in the bulk material, there are a lot of scattering. In 2D materials, because both side potential is very high now, because these electrons, they can move only in this direction, and when this confinement is there, they can move the very fast. Because of this one, in 2D materials as compared to the bulk material, their mobility is high, and when their mobility is high, basically we can use them for these sensing applications, and we get the fast response. Now this one is the first region. Second region is there here. We can understand this one is the our simple, this one field effect transistor is there. So I assume that you know this one, how field effect transistor is working. So in the field effect transistor, we have one source and another one is the drain. And now on the gate, basically, when we are applying the bias, here this conduction channel is forming. So this inversion layer is forming on, because this one is the p type material is there, and when we are applying this one bias above the threshold bias, here what is happening, this one negative, this one this top layer is inverted, that we call the channel is forming. And when this channel is forming, now the current flow is there between source and drain, otherwise very less, this one, or you can say almost this one is the off region is there, when there is no channel formation. So in the bulk material, we can say this one is the something, this one, this channel layer is there, this one is around 50 nanometer or 100 nanometer is there. So when we are having basically thick channel, that means we have the different atomic layers here. Now this one different atomic layers, and now suppose sensing this ion is coming near to this one here, what is happening? Some interaction is happening. Suppose this ion is giving the electron or taking the electron, or some interaction is happening. Now what will happen? This ion interaction, or you can say the impact is there, that one is only on the top layer here. Suppose this one is stopping. From here to here, your carrier flow is there. Here from left hand side to the this one right hand side, some carrier flow is there, and now when this ion is coming, this one is stopping this one. So now these carriers can move from the bottom layer. So there will be some change in our electrical quantity. If you are measuring the resistance or current here, there will be a change, because in this case here, these carriers has to move basically longer path as compared to this one. But as compared to 2D materials, what will happen in the 2D materials? In the 2D materials, we have only single layers or few monolayers here. So in that case, as compared to this one here, suppose this ion is stopping the electron, that means this one is not allowing. Now in this case, if this ion is not allowing the current flow, here what will happen as compared to this one here, we change. Yes, any question? So no. Okay. As compared to this bulk material, in 2D material, we are expecting basically this change in the current this one will be high as compared to the bulk material, because in this case in one layer we can stop this one current flow, but these carriers can move from the bottom layers here. And now in this case here current, there will be a this one change in the current, but as compared to 2D materials, this will be small. So this one is the another advantage of using these nano layers, nano seeds, basically these 2D nano seeds to make basically these heavy metal ion sensors. And what we can use, one thing is that we can use the 2D materials, but you know the growing these layers is very difficult. Growing these continuous layer is very difficult. So another way is there in few materials, basically here when we are making the heterojunction, here at the junction one 2D electron gas is forming. We can use this layer to make these transistors here. So for example, in gallium nitride and aluminum gallium nitride, this one, because of the polarization, what is happening here, one 2D electron gas is forming. We can use this 2D electron gas, and then we can make basically these transistors based here heavy metal ion sensors. So first we will try to understand, this one is called the high electron mobility transistor, HEMT. This one is the high electron mobility transistor is there. This one is also the one type of the field effect transistor here. This one is the field effect transistor. Same by the gate we are controlling. In this case also, we are controlling this carrier flow by using the gate here. But this 2D electron gas is forming at this junction between gallium nitride and aluminum gallium nitride. So when we are depositing this one heterojunction, at the junction basically this 2D electron gas is forming. And when this 2D electron gas is forming, that means here carriers can freely move this one at this junction. So first we will try to understand basically how this HEMT or how this 2D electron gas is forming. So we know if you can use these 2D materials, basically we can get the high sensing response as compared to the bulk material, because in this case the channel width is larger as compared to the 2D electron gas. So now here how this 2D electron gas is forming. Suppose if we take this one gallium nitride and aluminum gallium nitride. So this one is the conduction band. This one is our conduction band. Here this one is the conduction band, and this one is the conduction band of aluminum gallium nitride here. And now we know at the room temperature few electrons are in conduction band, because these electrons they get the energy at room temperature and reach from valence band to the conduction band. So in this case, because of this particular band diagram, or you can say the energy diagram, these electrons will try to basically this one go in the minimum energy states. And where is the minimum energy states? This one is the minimum energy state is there. So these carriers will trap at the heterojunction. These carriers trap at the heterojunction between gallium nitride and aluminum gallium nitride. And now these electrons cannot move in this direction, because here energy is higher. They cannot move in this direction. Here is also the energy is high. But in the third direction, if we can make, for example, source and drain in the third direction here, now these carriers, they are free to move in this direction. So here in the field effect transistor, basically, we are taking the advantage of these 2D electron gas, and we make these basically high electron mobility transistor. These are the advanced transistors we call the high electron basically mobility transistor. HEMT basically working principle is similar to the field effect transistor, only in these materials basically this 2D electron gas is forming. Now why this one is forming? Because gallium nitride is having the spontaneous and piezoelectric polarization, and because of this polarization, here we have the negative, here we have the positive charge. Now these electrons, they are trapped at the heterojunction and forming this 2D electron gas. If you want to see the complete basically, your energy band diagram. This one is the valence band, here is the conduction band, and in this minimum energy, basically here if you see in the conduction energy level, this one is the minimum energy, this one states are there. So these electrons, they are trapped here. So we can use these these 2D electrons, and then we can make these high electron mobility transistors. Okay, so this one is the concept, basically how these high electron mobility transistors are working, and now we can use these high electron mobility transistors basically to make the heavy metal ion sensors. Now, how to grow gallium nitride? Why we have taken the gallium nitride? One advantage is that in gallium nitride and aluminum gallium nitride, this 2D electron gas is forming. Another reason is that why we are not using the field effect transistor, silicon based field effect transistor. The reason is that silicon, basically we have to put in the water, and when this one in silicon will easily oxidize this one. Gallium nitride is stable in the harsh environment. Another case is that one is there in the field effect transistor, basically channel width is larger as compared to the 2D electron gas here. So 2D electron gas is highly sensitive to these ions, so sensitivity is higher. Now the another question may come, this one, why we are using only gallium nitride? Because same this one 2D electron gas is also forming in gallium arsenide and aluminum gallium arsenide, but you know the arsenic is toxic, this one, so we are not using for the water applications. So now how to grow basically these gallium nitride layers? So gallium nitride we can grow only by two techniques. One is the this one MOCVD, another one is the molecular beam epitaxy here. So we have used this one molecular, this one organometal chemical vapor deposition systems. This one is the MOCVD is there, and in India we have this MOCVD and MB only in 5-6 institutes. At IIT Jodhpur we don't have. We collaborate with Singapore, this one A-Star Singapore, they grow for us this one here, and this growth is not easy basically here. We cannot deposit by sputtering or other technique, this one. Reason is there because gallium nitride, these substrates are not available. We have to grow on the foreign substrate, and again this gallium nitride decompose before melting basically. So we cannot grow these substrates. So what we have to do, we have to grow on some foreign substrates here. And you know in the gallium nitride only in 2014 basically Nakamura and 3 professors, they got the Nobel Prize. They have grown by the MOCVD, this technique, and MOCVD and MB both are costly equipments. We have to spend around 10 crore, and then the maintenance is very high in these of these equipments, because we use in MOCVD we use the toxic gases, this one. So because of this one here, the equipment cost is very high. So what we have done in A-Star Singapore, they are growing these these sorry, these wafers for power electronics devices. So we use the same devices. So how they grow, basically on the silicon substrate they grow, they use the 1-1-1 orientation. Reason is there 1-1 orientation, and gallium nitride basically these are having the minimum lattice mismatch, because this growth is the epitaxial growth is taking place. Epitaxial means this grown your material and substrate basically they are ordered. Basically there is a fixed relation is there. Epitaxy came from the Greek word, so that means these atoms are ordered this one on the top of the substrate your atoms here. So now for the stress management, we have grown this one aluminum gallium nitride layers, and because we have to grow the high quality of this gallium nitride and aluminum gallium nitride, otherwise what will happen, if there are some defects, these defects can capture these electrons, and when they capture this one, these electrons cannot move freely at the heterojunction. So we have to grow the very high quality, and to avoid this one thermal mismatch and lattice mismatch, we have to do these managements here. And here you can see in the transmission electron microscopy TM images, this one easily we can find out these different layers: aluminum nitride, aluminum gallium nitride buffer layers, then gallium nitride. Again, this one is the gallium nitride, this one layer. And finally on the top, basically on the gallium nitride, we have around 1 nanometer aluminum nitride and then 18 nanometer aluminum gallium nitride. So at this place, this 2D electron gas is forming. And on the top, because aluminum should not oxidize, so we have to use around 5 nanometer of the Cape layer. This one is the gallium nitride Cape layer is there. For more details, you can refer this paper. And here, yeah, can you hear me?
Yes, yes, sir.
Okay, so basically these samples, they are grown on the 8-inch wafer. So you can see in the 8-inch wafer, we can get the many samples. So first what we have done this one on the wafer, we have done the by hole measurement, we have measured how much is that this 2D electron gas, this one concentration is there, and how much is the mobility is there. So mobility is around 1800 centimeter square, this one per volt per second is there. And here is the this one carrier concentration is there that we can measure basically here at the different points, because this carrier concentration is uniform or not, that also we can optimize. Next, we have basically we have to do these material characterizations, how is the growth is taking place. Also in MOCVD in situ also we can monitor how many number of layers we have to grow this one. So by that one is having the laser interferometer. By using this one, during this one we can monitor. And now another, because when we are growing on the large wafer, what is happening, there is a basically there is a bowing is there. Bowing basically wafer is there. This one is not uniform. So when we are doing the basically mass production, is very important. Our wafer should be the there should be no bowing basically. Otherwise, in the lithography there will be an issue. So this one here we have optimized. Basically, they have optimized for us this one. They have used the different these layers. And finally, we got this one very good. This one by using basically these parameters. So they have used around 390 to 400 nanometer with starting this one low temperature aluminum nitride layer. In that bowing is very less than around 50 micron is there. So these are the basically here growth parameters. Again by HRXRD here these layers are the highly basically C oriented. Gallium nitride orientation is C. Again, how much stress is there we can measure basically here. So almost this stress is relaxed basically. Only this aluminum gallium nitride, these are the initially layer, they are having the stress. But here this layer is the top layer and this one is the basically our gallium nitride. So they are almost stress free, but initially layer this aluminum gallium nitride only they are having the stress. But when we are doing this different layers management, we can grow the almost stress free layers. And the stress free layers means there is no this one, there are this one very less number of defects. Again, these layers were characterized by the Raman spectrometer. I will not go in the detail. These are the characterization by using this one. We can confirm this one. Whatever materials we have grown, that one is the high quality of gallium nitride and aluminum nitride layers. So one thing is that here, this one basically your device speed is decided by the mobility, how much mobility is there here. But another factor, if mobility is high, then also sometimes your device speed is not high. So here we try to understand this one. If mobility is high, why basically my device speed is not high. So we know in the aluminum gallium nitride and gallium nitride, here the mobility is very high at the heterojunction. So that means this device speed will be high. But still, if speed is not high, we try to understand basically speed is depending on what factors. So here I think all of us, we have studied this one here, this story basically, and today also this story is valid basically in the metro cities. You have very good car, but still basically your speed is decided by the red signals. Okay, your how many signals are there. So that means here, similarly in the transistors also, speed one definitely that is decided by the mobility, but again this one is decided by the contact here. How this one, how much this contact is forming, how much is the contact resistance is there. So if suppose your mobility is very high, but contact resistance is very high, in that case overall your device or system speed is there, that will be less this one, because speed is also decided by the contact here. Similar to this one, for example, someone is going by bicycle or someone is going by car here. We know the car basically capacity is very high, this one, but still this one speed is decided by the here lights, this one how many signals are there. Similarly here, this one is decided by the contact resistance, how much is the contact resistance is there. So first thing is that how to measure the contact resistance. We want this one between our semiconductor and metals, the contact resistance should be minimum this one. But how to measure this contact resistance? So mostly this one, I think, okay, how much should be your contact resistance? Only we study this one, this should be less. But how to measure this one? So I am going to talk about this one, how you can measure the contact resistance. Suppose you are working on some new material, and now how much is your contact resistance? And in the transistors, basically your resistance, contact resistance is very important. So what we have to do, we have to use this TLM method, transmission line method. And in this method, what we can do basically by lithography or by this one using the physical mass, you have to deposit the different basically contacts, these layers. So gap you have to you should keep in this one 100 micron, 200, 300 and 400 micron. So this one is linearly, this gap is increasing. Here you can see the optical photograph, and now you have to measure basically between this one is the 1, 2, 3, 4. You have to measure the current between different electrodes, between 1 and 2, 2 and 3, 3 and 4, and 4 and 5. How much is the your current is there with voltage. So this one is the your current voltage basically measurement is there. So you can grow these 5 contacts and then you can measure basically these 4, this one current voltage plots. Now from current voltage from the slope, you can calculate the this one how much resistance is there. So we can plot this one is the our resistance. Here is the L1, L2, L3 and L4. So we can use this one. L1 is 100 micron, L2 200, this one is the 300 and 400. And now we can plot basically from this one, from whatever resistance is there, we can plot, and basically from here we will get the contact resistance. And in this case, we got this one minimum contact resistance around 34 ohm per ohm, this one millimeter, this one. So what we have done this one here, what we have done particularly here, we have used the aluminum, this one chromium and this one gold. So we have used the tri-metals, this one, to minimize this contact resistance. Another one is the seat resistance. So how we can calculate from the slope, we can calculate this one, how much is the seat resistance is there. Here, how much width is there, our device width we know. So we can get seat resistance is around 230 and contact resistance is 34. So we have to get this one minimum contact resistance here when we are making the, we are forming the contact. Otherwise our this contact is ohmic, but contact resistance is very high. So this one is very important basically when we are making the contact. So next here, Once we have made the contact, this one we have optimized basically how much this aluminum, chromium and gold we have to deposit. So around here 150 nanometer aluminum we have to deposit, chromium 30 nanometer and 200 nanometer we have to deposit the this one gold. So this one is the our basically for the source and source and drain. So then we have to do the lithography, and this unwanted metal is there that we have to remove this one. And again, what we have to do, we have to do the RTA. So we did the annealing at 150 degrees centigrade for 60 seconds. Why we did this one annealing? If you see our, because top layer is the aluminum gallium nitride. So when we are doing the aluminum, this aluminum is diffusing through the aluminum gallium nitride and making basically, this one is making the contact with the 2D electron gas. After doing this one, here we have to isolate source and drain because we have to dip our sensor inside the water. So if source and drain both are open, there is high possibility this one between source and this one drain, this current this one can flow through the water, not through the device. Next, we have deposited the again this one gate, and for the gate we have used the Schottky contact. So we have deposited nickel and gold. Nickel is mainly for the adhesion purpose here because gold adhesion is not good on this one gallium nitride. So we have to deposit nickel and then gold. And here this is the our final device is there. How this device is, this one look like here. So this one is the gate, here is the source drain. We have to isolate. So we have deposited silicon nitride, and from here we can take these contacts basically. And how our final device look like, here you can see this one is the final device. We can take the wire, this one wires from here, we can do the wire bonding, another here. So this one is the source, here this one is the drain, and this one is the our gate is there. And now this device we can put inside the water, and then we can do the testing. This one is only the high electron mobility transistor. Still this one we have to this one functionalize the gate, whatever this one ions we want to measure, we can use the different functionalizing layer, and then we can basically make these transistors. Here these are the basically lithography steps. You can see this one we have to do the spin coating, we have to deposit this one photoresist PR, we do the pre-baking. After doing the pre-baking by the UV, we have to expose this one wherever we want to this one define basically our electrodes. So basically at these areas, for example, will expose this one, and here will be the PR. Next, what we have to do, this one we have to etch basically this unwanted here, because this one is the photoresist is there. So we have to remove by etching method. We have to remove the our, because we have to use the three etchant for gold, again chromium and aluminum. We have to remove these layers here only. So here this one is the after removal of the photoresist, we get the source and drain. So this one is the first step is that how we have to do. After doing this one, again another lithography step we have to use to define nickel and gold, and here we have to use this one silicon nitride. So there are this one multiple lithography process to fabricate basically this device. This one is the optical image is there. So here is the basically source, this one is the drain, and this one is the here is the gate, and this one is deposited the on the top. This one is basically silicon nitride is there. We have isolated the source and drain, so only gate is exposing in the water, not this source, this one source and drain. Next, what we have to do, once we have fabricated this one, particularly we have to use some functionalizing material here. For example, if you want to this one, since the mercury, here again we have to use some nanomaterial that can absorb the mercury. And once we functionalizing this one, then we can put in the water, or we can put the water drop, and then we can monitor the this one current between source and drain, how that one current is changing. So how we are doing the measurement by the from the source meter, here we are applying some constant voltage, 0.5 volt, and then we are monitoring our ID current is there, how this one is changing with the ion concentration. So we can drop the different ions basically in this one and can do the measurements here. So here I'm going to talk about this one, our recent work. One is the mercury sensor, another one is the lead ions. So how to detect the mercury? We know the mercury is highly toxic, and this one, at least this one, our level should be the less than the 5 ppb here. If this one is above 5 ppb, is highly toxic for human health, this one. So here basically we can detect this one. Here we have to detect this one. Our mercury level is there, that one is the less than this one, at least 5 ppb is there here. So to make this one, again we have used the 2D materials, that we have used the MOS2 here. So MOS2 basically, if you buy the bulk material, cost is around 500 rupees. We can get from Alpha or Sigma Aldrich. But if you buy only one monolayer of MOS2 around 1 centimeter by 1 centimeter square, this cost is around 50,000 is there. And now all this bulk material, if you separate out, or you can say if you make basically these layers here, approximately cost will be the 1 million rupees. So how to be, this one make the money from 5,000 to 1 million just by separating these bulk material into the monolayers. That means here our process is that one is not easy. Otherwise, easily we can separate out and we can make the money. And if you can make easily this one, again the cost will come down. So that means our growth procedure is that one is the complicated. So how to make this one? These MOS2, because our transistor is there, and transistor basically that one is ready, that we know this one how to fabricate this one, and we have fabricated. So next step is that how to synthesize basically these functional material, and third step will be there, once we have synthesized, how to transfer this material on the gate here. So what we are doing, this one at IIT Jodhpur, regularly we are depositing this MOS2 material. But how we are doing? We are doing by the chemical vapor deposition by the CVD system. So we have, this one is the 3-zone CVD system is there, and we grow the different, this one nano structures, this one flex, horizontally aligned, vertically aligned, even nano wires, and this one we grow the different morphologies here. You can see the very nice flex basically. But this growth is taking place at higher temperature. So minimum temperature is around 850 degrees centigrade is there. And once we have defined basically source and drain, now we cannot, this device will not sustain above the 300 degrees centigrade. So to grow these MOS2 basically, we cannot use basically chemical vapor deposition system. So we have to look for the some alternate method here. So we have used this one hydrothermal method is there. This one is the, again, the low cost method is there, and low temperature method is also there. So we use the MO3 and thiourea, and we have controlled the pH by using the NaOH. And then this one is that we have to keep around 24 hours at 200 degrees centigrade, and finally we get this one black powder, this one. So our starting material is the mainly MO3 is there, and here we are getting the MOS2, this one. So first thing is that this black powder is MOS2 or something else here. We have to characterize this one. So we have done the Raman, this one, spectroscopy and X-ray diffraction, and from both these techniques we found this one basically, this material is the MOS2 is there, this black material is there, this one is the MOS2 material is there. Next, what we have done the electron microscopy images, and you can see these are the very nice flakes basically here. And for the sensors basically, this sensing phenomena is happening on the surface. So surface area is very important. So you can see in these flowers basically, these are the plates basically, these nano seeds are there. So overall the surface area is very high, and when the surface area is high, what will happen? When surface area is high, basically these nano seeds basically, they can absorb more number of ions, and when they can absorb more number of ions basically, overall our sensing response will be higher than the single layer. So these basically these nano seeds basically they are very useful for the sensors. So next this one, once we got this black powder, we have dispersed in IPA, did the ultrasonic, we have transferred basically on the gate. This one is our fabricated device is there. So we have transferred this one MOS2 on the gate here, and here this one is the final device is there. Then we have done the testing. I think you can see here some more images basically how we are doing this one. We are isolating this one. This one is the glue. Here we do the wire bonding. These copper wires we have to take from the source and drain, and we use this one silicon glue to isolate basically, because this complete system we are putting inside the water. So here you can see the some more images. This one here, this one is isolated. Now only here this gate area is there. This one is the open. Here you can see the more this one closer views here. So this one is the source drain, and here is the gate. So you can see this black power. This one you can see this one is the particularly MOS2 is there. So MOS2 is uniformly distributed on the gate here. So next we have done the sensing. These are the characterization basically after transferring on the gate. When we are transferring, how is the distribution? You can see these basically these MOS2, these flakes are uniformly distributed on the gate here. You can see the cross section view. This one is the Raman spectra is there. Next, what we have to do, we have to measure basically how much this one current flow is there. So from here, this one is the basically inside the water. We put this one and we have measured the basically current voltage characteristics. So this one is for the bare device. After transferring MOS2, this one has reduced, and when we are putting basically the mercury ions basically in this case here, this current has started the decreasing. And if we see this one, when we are applying this one constant voltage between source and drain, and if we monitor this one current basically, what is happening? Initially current is constant, and once we add basically some ions, is slightly increasing basically when we are going in the PPT level. But when we are coming in the PPB level, here current will start the decreasing. Here you can see current will start the decreasing here. So that means there is a change in the our ID current with the with the ions concentration here. And how much change is there? These parameters we can extract this one. So this one is the sensing mechanism. Why initially this one is current is increasing and decreasing. This one you can see in this paper we have published in the Sensor and Actuators B. So next we have done the selectivity test. This one is the mercury. We got very less response from copper, cadmium, and chromium, and here almost this one from other ions almost negligible response. Also we have done the cross selectivity. In the cross selectivity, what we have to do, we have to mix all these ions together, and because in the water we don't know this one what ions are present, so we mix all the ions together, and then we do basically how much is the change in the current is there. So almost this mixed ions response is equal. This one almost equal to the mercury ions response. That means this response is coming only from the mercury ions. Sensitivity is very good, around 0.64 microampere per ppb. How much is the linear detection range is there? That one is around 0.1 ppb to 100 ppb. So what is the role of linear detection range particularly? When we are using the linear detection range, that means our transfer function is there between the input quantity, that one is the mercury ions, and output, that one is the current basically. So in that case, if linear relation is there, in the linear relation, we know when we are doing the sensor calibration, we required only two standard point here. So when linear transfer function is there, basically we need only two calibration point. By calibrating at these 2 points, basically we can define the transfer function. This one is the advantage. So overall we can reduce the cost of the sensor, and mostly because 100 ppb of mercury ions is very higher side. So generally we need the sensor from 0.1 to 100 ppb range. Another, how much this one quantity of MOS2 we have to transfer. So what we have done basically, we have used the different concentration. We have used 10 mg per milliliter, 20 mg per milliliter, and 40 mg this one per milliliter. And we found initially this one is increasing, but 20 milligram per milliliter is the maximum where we got the sensitivity. Also, detection limit is also the minimum. When we are increasing, there is not much improvement is there. So here you can see these data at different concentration, different basically concentration of MOS to this one here when we are loading on the gate here. So almost we got the similar behavior. Next, what we thought in the this one purifier, generally we have this one UV lamp, and this UV lamp is mainly for to kill the bacteria here. So we thought where to mount basically these our sensors. Can we mount near to this UV source? So we have used one UV source, this one, and then we have done the sensing. And when we have done the UV source, this one, we got very good response. This one, you can see our current is there. That one is in the milliampere. If you remember this one in the previous case, without this one UV source, current was in microampere. But here change, because if current is very high, easily we can detect this one. And even we can detect 1 ppt also. That was not possible in the previous case, and as per WHO defined limit is around 1 ppb is that. So change in 1 ppb easily we can detect this one. And here the sensitivity is around 548 microampere per ppb. That one is very high, this one, as compared to the this one without UV source. Again, here you can see the linear detection range is almost similar this one. And if we see the sensing response, basically the sensitivity is around 850 times is higher than the without UV. So just mounting this sensor near to the UV lamp, because in water purifiers basically we have the UV lamp, and if we can mount near to the UV lamp, basically we can improve the sensitivity around 850 times higher than the without UV. So next we thought when we are using the UV light, what is happening? This MOS2 is absorbing the light basically and improving the conductivity. So from that we thought if MOS2, if we can improve the conductivity. So how we can improve the MOS2 conductivity? Because MOS2 is the 2H phase. In the previous case we have taken. So MOS2 exists in the two phases. One is 2H is the semiconducting, 1H is the metallic. So what we have done, we have synthesized again this one mixed of 2H and 1H, this one 1T phase here. So 1T is the metallic phase, 2H is the semiconducting phase is there. So some here, some part we have the metallic, here we have the semiconducting. So what is happening? This electron transfer, because ions is coming, this charge is transferred on the gate immediately when we have the metallic phase. So we have again synthesized this one mixed basically here 2H and 1T phase, and then again we have fabricated. So here you can see this one is the gate basically, and how VGS and your ID plot is there. This one is the again confirm this one is having exist 2H and 1T phase by doing the Raman spectrometer. And one more additionally we have introduced here, that one is the basically gate bias. On the gate in the previous case we have not applied any bias, but here we have applied the bias also. We have seen the biasing effect, and when we are applying the biasing, basically at least we can improve this sensing response. Here you can see how much there is a change in the current here. So we have done this one here, you can see is at the zero bias. This one is when we have used the additionally this one biasing, we have used around 3-volt biasing. And by using this 2H and 1T phase here, we can improve the sensitivity around 520 times higher at the 0-volt. So just by mixing these nanomaterials, because we have tried only this one 2H phase and 2H and 1T phase, we can explore many more materials for the different heavy metal ions. These are for these heavy metals. Another here, what we have done basically when we have applied this one additional basically voltage around 3 volt, we can improve again the sensitivity around this one, around 850 times this one higher as compared to the MOS2 here. So by introducing this one also we can improve basically, we can improve the sensing response here. So 850 we got with UV, and without UV also almost same we can we can improve just by introducing these materials. So next we thought this one, if by conductivity, if sensing is improving, intentionally we can use some metal nanowires or nanoparticles. So easily this one silver nanowires are easily available. So we have made the composition of silver nanowire and MOS2, and this ratio we have taken 1:4. We have tried all the ratios, but we got the highest sensitivity when silver nanoparticles are in the ratio of 1 and MOS2 they are in the ratio of 4. And then we have transferred basically, here you can see the composite, this one here, these are the nanowires easily can be seen, and these are the MOS2 basically, and we have transferred this one on the gate here in between source and drain. And then we have done the measurement, and we found this one here, we are getting the very good response this one here when we are changing these concentration. And here this one is the selectivity test is there, and the sensitivity is there. In this case is around 1.6 milliampere basically per ppb is there, and detection limit is also very low. Here we can see one this one PPT also we can measure, and 1 ppb there is a very good enough change is there in the milliampere, so we can measure easily this one here. And this one is higher than around 2005 times here, higher than MOS2, and 3 times higher than the 3 UV. So by intentionally introducing these metal, this one nanowires, we can improve the sensitivity. Also, we can explore some different nanoparticles. This one, so far we have done only these silver nanoparticles. So this one is the mercury. Here we have made the mercury detector, and next we are working on the lead ion detectors, because near to Jodhpur we have the Pali, and Pali is famous for the textile industry, and they are using many lead based dyes. And when they are using this lead based dyes for the color purpose here, they basically release this water in the river. Here you can see, we can make out this one is highly polluted is there, and this one is having the highly this one lead ions. So now how to monitor this one, how much percentage of lead ions are present in this water, because this level here is very high, this one lead concentration is very high here. So what we have done to basically, this one is the our societal issue is there basically. So how to detect this one, because again this water when rain is there mixing with this one, and wherever we have our lake or this one river, this one is mixing with this one and destroying our drinking water resources. So for this one, we have used one another 2D material. This one is called the graphitic carbon nitride is there. Here you can see the structure is having carbon and nitrogen, how they are basically bonded. You can see in this case here. We have used graphene, this one graphitic carbon nitride. Also we are trying, this one is the another, this one is the sulfur basically doped. We are also doing in the this 2D material some doping, and then also we are trying to modify this one, and we have done the sensing, and we got the very good response this one by using the graphitic nitride this one to detect the lead ions here. And here you can see the sensitivity is very good in this case, around 0.5 this one 532 microampere per ppb. And if you see the selectivity, as this one is highly selective to the lead ion here, we have not received any response from the other ions. So by using this graphitic carbon, this one carbon nitride, we can make the highly this one selective lead ion sensors. So then what we have done, we have tested, because in Jodhpur we get the drinking water from the Punjab from around 600 kilometers. So we have tested, we have collected the water samples from our lake. Then because some initially, because sensor we are using, so this one is highly sensitive, so we have to use some filters. We have used PDF filters, this one. Then we have filtered basically this water, and then we have done the sensing. So we have used, one is the our laboratory DI water, lake water. Another we have used the lake water, and third intentionally we have added the lead ion, and then we have done the tested. So this one is the Jodhpur lake water status is there. Almost this one is the lead free is there. These heavy metal ions, they are not present in this one here, but when intentionally we are mixing this one, there is a change in the current basically. So this one change in the current. So we can say this water is the drinkable. Almost this one is the lead free water is there. We are also trying to make other this one cadmium ion sensors as per this one requirement here. But again, we have to play with the chemistry. So far, we have used this one for this one, some this one chemicals, this one MP and GSH. I am not from the chemistry background, so we take this one whenever we are looking for new materials for different materials, the different ions. Basically, we have to take the help from the chemistry. So they have suggested basically this GSH is there. This one is attaching the cadmium ion, but this one is having the poor adhesion on the gold. So to this one to make this one to make decorate this one gate, basically we have to use the MPA intermediate layer. So you can see this one, because this one is not making bond directly on the gold. Here sulfur is making the gold. This one is the gold sulfur bond is there. So we have to use this MPA, and then we have to use the GSH molecules here. And sensing phenomena is almost similar this one, and here we got the very good this one response. This one even we in easily we can measure basically in the ppb range here, because cadmium limit is also higher side. We have to detect this one around 50 ppb is the WHO defined limit is there. Another important parameter I forgot to discuss, that one is the basically how much is the sensing response is there, because for the real time monitoring within few seconds we have to get the response. Otherwise this one we cannot do the real time monitoring. Suppose our sensor is giving response after 10 minutes. Okay, in 10 minutes whatever our drinking water is there, we are basically we are taking from the water purifiers in 10 minutes. So immediately 4-5 seconds is okay, or 10 second 20 second we should get the response. But our sensor is highly this one, or you can say the very fast, within a 3 seconds we get the response this one. So that means we can do the real time monitoring. These are the plots basically. In this case also we got the very good this one sensitivity. Only some issue is that with the selectivity, because we got some response from the other ions are also. So we are doing modifying this one, how to make this one highly selective, or by using some data analysis, because we can mount all the sensors together, and by using some AI and this data algorithms, we can separate out this one how much percentage of these ions are present. So again, because this is the sensor part, we are connecting with the this one IoT platform, and by the Wi-Fi we can send the data on the mobile. And our ultimate target is there to fabricate all these sensors on a single chip, and then we can connect basically, for example, wherever lake or this one our river monitoring is there at the different point, we can install these sensors, and through the this one Wi-Fi modules basically we can monitor this one real-time monitoring. We can do how this water quality is there, that one is changing. Suppose if some industry people, when they are releasing these ion concentration will increase, and easily we can monitor basically this one, and we can stop this one here, this highly contaminated water basically we should not release in the rivers particularly. So we can filter out this one, and then we can do, but again the filter out, that cost is very high. That's why these industry people, to save the money, just they release the water inside our water resources without doing the filtration. So in summary, I would like to summarize my talk. Basically, we have fabricated this high electron mobility transistor. Also, I have explained how this high electron mobility transistor they are working, how we can use for to make these heavy metal ion sensors. We can improve their heavy metal ion sensors sensitivity and selectivity by decorating with different nanoparticles and using the different approaches. And so far, we have fabricated mercury, cadmium, and this lead ion sensors here. So I have explained basically how these ion sensors are working. I would like to acknowledge first A Star Singapore because we have the collaboration with Dr. Sudhir Ranjan Tripathi and we get these wafers from them. And here we have a very good fabrication facility. And this work mainly was started by my first PhD student, Dr. Adas Nigam, and now he's doing the postdoc. And Nipun is continuing this work. And of course, for the funding, this one is the SCRB. They have given the funding to continue this work. And thank you very much. And if you have any question, you can ask me. And whenever you visit to Jodhpur, please visit to IIT Jodhpur. We have a beautiful campus here.
Thank you so much, sir, for such a wonderful presentation. Dear participants, if you are having any query, you can ask the expert directly or you can write down in the chat box.
Yes, please. If you have any question, please ask. Please unmute and you can ask me.
Participants, if you are having any query, you can ask or write down in the chat box, please. Oh. So I want to personally ask one question. You are using these sensors for the heavy metal ions. Have you tried these sensors for some organic contaminants like pesticides or something?
That basically this one is working on the ions. If they have some ions, definitely this will work. Only we have to change only the functionalizing layer. So we have to see basically first what type of the ions they have. So a pesticide, if they don't have any ion, then very difficult.
Okay. So in case of pesticides, I think there's some organic functionalization will be needed.
Yes, definitely. Because we have to absorb these ions, and when we are absorbing, because here principle is very simple. Because this one we have to.
The echo is coming in your voice. I don't know why suddenly. Yes, sir.
Yeah. So basically, what is happening when these ions are coming, they are creating the potential here at the gate, and because of this potential, 2D electron gas concentration is there. This one is changing. So we can say one is the aluminum getting the arsenide, that one is the nitride, that one is having the higher this one band gap. So we can consider as an insulator. So the insulator one side when we are applying the this one potential, what will happen? Another side, this one opposite charges will generate. So this carrier concentration will increase or decrease. Because of this one, here this current is there between source and drain, that will change. So what is happening this one in pesticides, we have to see which pesticide is there and what type of the ions they are having. And if they have the ion by organic material or inorganic material, how we can absorb.
Okay.
If we can absorb them, definitely we can detect.
Okay, thank you, sir. Participants, any other queries? Anyone?
Yes, I think someone raised the hand. So yeah, please unmute and ask. Dr. Pankaj.
Dr. Pankaj, if you want to ask, you can ask. Unmute yourself.
You are not audible. You have unmuted, but you are not audible.
Uh, so let me see.
Yeah, he has unmuted, but not audible. Yeah, you can type your question.
Dr. Pankaj, you can type please in the chat box. I think there is some voice echoing system is coming in between. Dr. Pankaj, yes. Queries can be written in the chat box. Anyone, if you have. Not audible. My voice is audible to you?
Yes, you are audible.
So from your side, some echo is coming from the microphone. Okay, one of the participants have asked, can we fabricate one molybdenum nitride with different nanomaterials for different pollutant sensing?
No, that is by one. This I think this one is a most too. So this one is not possible basically because one material cannot absorb this one. If this can absorb
The
particularly,
echo is coming from your side. I don't know why.
this one is coming from starting or now has it started?
Now, yeah, the whole lecture was fantastic, but now in the suddenly when I told to you,
Just
then echo start coming.
yeah, just a minute.
Yes, sir. Yes.
I can use the 1 minute. Give me a 1 minute.
Yes, sir. Sure, sir.
Hello. Can you hear me?
Yes, sir.
Now it's clear?
Yeah, yes, sir. Now it's clear.
Okay.
So the question is, can we fabricate one molybdenum nitride with different nanomaterials for different pollutant sensing?
Yeah, if you are mixing with different nanomaterials, definitely this one is possible. But if you are using only MOS2, then is difficult. I think this one is not MO2, this one is MOS2. So with one, because if this can sense basically different this one ions, then our sensor is not selective because we want to make the sensor selective.
Okay, another question, sir. How physical, chemical, and biological sensors are different in construction?
Oh, construction, we can make biosensor also. Same by using the, for example, cancer cells. People, this one researcher, they have used the same structures. So we can make definitely biosensors. Chemical sensor also we have tried. We have made recently NO2 gas sensors by using the same. And bio, because we don't have expertise, but we may explore this one bio also because many researchers already they have used the same platform.
Okay, sir.
Okay. Chemical, yeah, gas sensing we have tried basically, and we got this one here. We made this one NO2 sensors by using the same platform.
Okay, sir. Any other question? Anyone participants? Can we develop nanoparticles without sensor development?
Yeah, that is possible. That is possible.
First,
Sensor is,
nanomaterials are created and then sensors are created.
yes, sensor is the basically application.
Yes. Sir. Any other question of any other participant based on sensors or nanomaterials? Okay, sir. In case of no question, I heartily thank you once again for such a wonderful session. We have learned a lot about the nanomaterials, basic synthesis, their main characterization, how they can be applied in the sensor technology, especially for the reduction of water pollutants. Thank you so much, sir, for sparing time in this FDP.
Yeah, thank you so much. And if anyone has any question, you can write me this one. I'm happy to answer that. And thank you for inviting me for this talk. Yeah, thank you.
Thank you, sir.